All right, once again, I am Scott Jenkins, Senior Editor at Chemical Engineering Magazine. We're going to get started with today's webinar, so welcome to everyone. Today's webinar is going to be on overcoming real-world obstacles when calibrating temperature instruments. Our speakers today are Roy Tomolino and Ned Espy of BMEX. Ned and Roy are going to take us through some of the difficulties technicians face while calibrating in the field, and also share some calibration hacks to improve the calibration process for those doing it, while also improving the results. Before I introduce the speakers, though, I just need to get to a few housekeeping items. The sponsor, the speakers, and the hosts would all intended this event to be a conversation, so we encourage your participation. That will occur in a couple of ways. There'll be a few poll questions during today's webinar. So when we get to those, we encourage you to respond to the questions using the polls tab on your GoToWebinar control panel. There's also going to be a question and answer session at the end of the webinar, and attendees are invited to submit questions during the presentation. To do that, you type a question into the questions tab on the control panel. If you need technical support during the presentation at all, there's also a chat tab on the GoToWebinar panel, so you can use that for tech support. But for all the content-related questions, we want you to use the questions tab. And lastly, at the end of today's program, there's going to be a survey. It will pop up in the web browser at the end, and you can provide feedback about the webinar. So getting on to the today's topic, our first speaker today is going to be Roy Tomolino. Roy's been teaching calibration management for over 2 decades. Throughout his career, he's taught on 4 different continents to people from over 40 countries. His previous roles include technical marketing engineer and worldwide trainer for Hewlett-Packard and application engineer with Honeywell. Now, Roy is responsible for all BMEX training activities in North America. We're also going to hear from Ned Espy, Technical Director at BMEX. Ned's been promoting calibration management with BMEX for over 20 years. He's helped develop best practices for calibration with a focus on pressure, temperature, and multivariable instruments. He's a consistent editorial contributor to leading industry publications, and he's received several significant recognition within the automation industry. Currently, Ned teaches calibration best practices and provides technical support to end users and to the BMEX sales team in North America. So with those introductions, I'm going to hand off the program to Roy and Ned. Guys, please go ahead.
All right, hey, thank you, Scott. So welcome everybody again. And I do think it's kind of, I don't know if it's inappropriate, but when we talk about issues with calibration issues, and then I get brought up here. So apparently I'm one of the calibration issues, but I'm okay with that. Temperature. One of our sources for information on calibration and temperature is right here, Calibration Essentials. There is a link, you can download this and add this to your knowledge base. So where we're heading as far as today, we're going to talk about some tips and tricks, oftentimes referred to as hacks. And we'll use a temperature source as well. And we'll use a real scenario, a calibration loop. This was brought to us by one of our customers. And it's having to do with calibrating 3 different things. And we'll show you how to calibrate 3 things at the same time. I know you're thinking that's not possible, but it is. Different parameters. We'll talk about standard RTD curves. We'll talk about Callendar van Dusen and ITS 90, whatever those mean, and what we've learned. We will cover that as well. So, Ned, what do we have coming up next? Do we have a question for everybody?
Yes, we do. Thanks, Roy, for starting us off. So we do want to ask the audience, we just want to get a feel for who's out there. So if you don't mind, punching in your role in your current position. Give us an idea of who we're
All right,
talking to
manager,
today.
supervisor, technician, engineer, vendor, or other.
So Roy, you definitely are another.
I think I resent that.
Yeah, yeah. If you take the poll. So we're waiting for the results to come in. We want to give you guys a little chance to figure out how to click. So hopefully we're seeing some things.
What is your role at your current job?
Yeah, evangelist isn't on the list.
What? Okay. Definitely other then. All right, so almost half are engineers. Okay, so we were guessing that maybe a quarter would be each of them, a quarter manager, technician, engineer, and vendor, or that was my guess starting off, but almost half engineer, 22% manager, supervisor, 20% technician. Was that the next one?
Yeah,
I didn't catch the number on
sorry.
the vendor. 2%, okay, and 10% other.
All right. All right, so we have a good balance today. Great. Okay, so we do have a little demonstration we want to do, but I guess as an overview, Roy mentioned the word hacks. We just want to try to provide really what I call practical knowledge. So, and it works both ways. I think everything we're going to talk about today, we've learned from the School of Hard Knocks. So customers have taught us a lot of stuff.
Yeah.
And I think in this instrumentation world, we all need to, to pass it on and encourage this as a career for young folks and stuff like that. So
And with that,
hopefully
every time we go out and we're in the field or we're in front of a customer, we learn something. And
that's true.
That is a good thing.
Yeah. Yeah. So hopefully we'll learn something today with some of your questions and input. So the scenario we have, and this is a real request. I was helping a customer at a chemical plant in New Jersey, and then just within a week, an Iowa food processor had a similar temperature application. So, both of them use a paper form that they develop. It's probably in Word or Excel, and they write these numbers down. But the procedure is to pull the RTD from the process, put it in a dry block, and test it at 3 points over its range, really related to the process. And then also record the milliamps and the readout in the control room. So here's kind of here's what we have. We have this temperature element connected to the transmitter with 4 to 20 going into the input card, and then ultimately displayed to an operator.
And if I could just explain, when I said that we're going to do 3 things, number 1, we're providing temperature to this temperature element or a temperature probe. That's one thing. And number 2, we're measuring the milliamp output of that transmitter. And number 3, we are recording the value on that DCS display in the control room. 3 things.
Right. So our critical readings are going to be this temperature here, the milliamps coming out here, and then this display here. All right. So how are we going to do that, Roy?
Well, I'm not really sure, but are we really going to do this at 0 degrees?
Well, note that with this demo, before I launch into it, we're going to show you 2 hacks. And the first hack is to go to 0 degrees Fahrenheit. Takes a long time. And so I asked the customer, I said, do you really go down to 0, that far below freezing? And they're like, no, not really. It really never gets below freezing, actually. So you should explore this concept. So we're actually, instead of doing a 3-point test, we're going to say, hey, let's check it at 40, kind of a low possible temperature, and then 150. We'll do 2 points and cover the range of this transmitter over the real operating temperature that it sees.
Okay.
So
So
it saves time.
so the first benefit you're talking about is the transmitter is ranged to go from 0 to 150, but in reality, 0 isn't feasible, or it's not realistic, and you're going to spend a lot more money getting something to take you down to 0 degrees Fahrenheit. So you're saving money by a less expensive standard, but you're also saving time by doing 2 points instead of 3, temperature being rather linear. So well done.
Right. So so it's always good to take a step back, and maybe this is what you've always been doing, and some engineers set the range up this way before the plant was even built, and
Yeah.
it's just not practical. So anyway, let me turn on, let's see here, I have to make a little click here. So I have a camera. So here's my office. And
Why
by the
is
way, I
there a
have,
moose in your office?
this is my calibration moose, and he's observing us, Roy, to make sure that we stay in line. But this is our dry block. So I've got 2 temperature probes inserted in this block. And let me give you a little tour. I know it's a little out of focus, and I have a spotlight here. But this RTD coming out is connected to this little transmitter down here. It's a 3-wire connection.
Okay.
And then the leads are coming out, and we're connecting to the milliamp meter that's built into the dry block. So we're measuring milliamps, and we're powering the transmitter. And remember, I said we had a reference probe. So this skinnier probe gives us accuracy out to the second decimal. So that cable is plugged in here at this LEMO junction. So for this calibration, we're going to be comparing the LEMO connection measurement to the milliamps that you see on the screen here. So any other
All right.
questions, Roy, on that?
So we have a probe under test, and then you have another temperature probe that's even more accurate, and so that is actually our temperature standard.
Correct.
Is that what you're saying? Okay.
Exactly.
And I got a bit of vertigo from that camera work. Can we work on that a little bit?
Yeah, I'm not a cameraman, sorry.
Okay.
So I have this other tool. So here's the display on the calibrator, but I have a way to show it on the screen. So here's my temperature, and remember I said we were going to go to 40. So we're sitting here at 39.989, and we're getting this odd milliamps out of here. And if I tap here on the screen, I had to wake it up. My set point is 40. So my internal temperature reference is trying to control to exactly 40. But remember, I said my traceability is coming from this reference probe. It's called the IPRT 300. So it's sitting here close to 40, but it's actually saying true temperature is a little bit lower. But here's the milliamps for the 0 to 150 range, and it's plotting right here. So it's within 1/10 of a degree. So it's really pretty good. So let's hit start to begin this test. And I have a little countdown going on here. So it's going to record these 2 numbers in the calibrator's memory. And now it's presenting me with the readout. So this is called a group calibration.
So this is our DCS display. What are we seeing on that DCS?
Yeah, so now there is a little glitch. The dry block stopped controlling for a moment, so the temperature is running up, but it's still pretty stable. So just for expediency, I'm gonna click through here, but at this point, I would call on the radio and say, hey, control room, what do you guys see? And the guy tells me, oh, it's 40.3 right now. So it's off. In fact, it's off by 0.3 degrees to the low side, where it was 0.1 degrees on the high side. So I'm going to accept that.
Okay.
And the calibrator's not happy because we lost that control, but
That's okay for this.
now we're going to flip back to the probe, and now the set point is 150. So
how do you know that the set point is 150?
It's right down here, and the expected milliamps at 150 is going to be 20. So it's kind of, this is our target, and this gray line is the scale. So this, you can see this is 0 to 150 over the range, and our first test point occurred here around 40 degrees. The plots off the graph, we're seeing a difference of 2 degrees now between the milliamps and the reference probe that's in the dry block. So the temperature probe's moving pretty fast, but not as the milliamps are moving slow here. I guess these are they're kind of moving together, but we have another view here. So let me click up here. So there's a bunch of lines on this graph, but we were basically at 28% of range, whatever 40 divided by 150 is. And now the temperature's taking off, trying to get to 100% of range. But it's plotting 3 things here. So if I click, it's showing that the instrument input is my traceable reference probe.
Okay.
The controller set point is this blue line. And this is actually the controller temperature here. So the controller temperature is moving the fastest compared to the reference probe. And then the last element is the milliamps. So here's the milliamps, and it's moving, it's kind of tracking in parallel with the reference probe. So, you know, with a dry block, the internal sensor is mounted very close to the heat source, and it's a small mass. My reference probe, the red line, is a 1/4 inch diameter, so it takes more energy and more time for it to reach this temperature that this guy is sensing.
And plus that insert has to heat up itself, and that's more mass. So that does make sense.
Right. So one of the things, I already had it set at 40 degrees, but it would have taken around 10 minutes to get from 72 degrees in my office down to 40.
Okay.
If we had tried to go to 0, it would maybe take 15 or 20 minutes. So we really, you know, are saving at least 20 minutes of field time by just doing this 2-point test.
And one thing I'd like to point out is we are doing a 2-point test, but we're also doing a group calibration where we are recording 3 different things: the temperature for the probe, the milliamp output, and the DCS reading. If you didn't need a loop calibration like this, you could calibrate the probe and the transmitter milliamp output as a completely automated process where you press start and it does everything, all the measurements, all the recording, and you walk away and you come back when it's done. Because we do have this DCS display, there is a manual intervention where we have to punch in what the DCS is showing.
Thank you. Yeah, thanks for explaining that. So, but no matter how you do it, you know, our customers are using forms, and all we did was write down the 39.988 and the 8.2 whatever it was milliamps, and then we called the control room, and they only see the temperature out to 1/10 of a degree, so we recorded 40.3, which is what they told us. So you know, we're doing it in a paperless mode, but certainly you could use tools that you already have and create the same data. So we've been talking now for 4 minutes since we made that first recording, and we're getting there. We're now seeing 100% on the graph. We're at 100, almost 130 degrees. So everything's moving along here pretty good. So we should see this start to level off somewhere around 145, it'll start. So we're giving it 100% heat right now. We're giving the insert as much heat as we can deliver with the dry block here.
Okay.
And there's another thing that we're showing here. So this is showing the actual temperature measured by the internal control, but we also have this 2 sigma calculation going on. So we're looking at stability. So this is like a 2-minute integration of the readings, and it's a delta of 10 degrees. So going back 2 minutes, it was 10 degrees lower than it's seeing now. And but as we get closer to 150, and these 3 curves, these 3 lines start to flatten out, the stability number is going to drop. And in fact, we want to see it below 1. So our stability graph is just showing a factor of 1, and it's showing that the transmitter is actually pretty stable, and that's because I have some dampening on it. I put, I think, 1 second of dampening on it, so so it's not moving as fast as maybe the temperature probes are. But again, temperature is kind of a slow-moving parameter. Anyway, so now you can see the stability starting to drop.
And
if I go back to our,
you can also look at it as a confidence level.
Excellent.
And as you predicted, around 140, the temperature started to decrease so that it doesn't keep ramping up as fast. We have a set point of 150. We're trying to land right on it instead of overshooting it to save time.
Right. And the stability line should appear here when this drops below 1. It'll show up on the graph here very soon. So, you know, as a technician in the field, you want to take your readings when everything's really stable, especially on temperature. So like you say, it adds a level of confidence to the work you're doing, and it's just helping us out here. So there's the stability graph. So the small blue line just popped in, and it's fast. It's dropping very quickly here, and pretty soon we should see a red line come in for the reference probe. So these things kind of work in parallel here. So we'll come back to this screen, but let's look over here. So because of this lag, we're still showing error of over ½ degree. And by the way, this is a pretty tight tolerance here, ½ degree. So it's kind of pushing the limits of the equipment we have today. But look, it's getting closer. It's catching up to the milliamps, and now we're less than ½ degree error, and it went green. So the fact that this is still moving, we want to wait. You know, we want to wait for things to get a little more stable. So here's the reference probe. It's reading 150.156 or 1.16, and our controller overshot a little bit. It's above 150, but now it's starting to come down, so it's trying to settle. But here's our stability lines. They're all coming down very close to 0. So so it was pretty close here, but you know, after 1 minute, we're seeing the lines really close together here. And let's look at this. So I'm going to let the dry block do it. I could hit force accept, but very shortly here it should record.
And what stability do you think it'll take it?
It's really close to 0. I don't know. It needs to get. It's already below 0.5. I think it might even get to 0.0 something. So it's been stable for 1 solid minute. So we're gonna have to talk for another minute, Roy. But you can see So depending on how accurate you want to be, so maybe the chemical guys would be happy, but maybe the food guys, if this is a really critical temperature and they're going to this much trouble, they might want to really wait and get a good reading. So now the stability is almost a 0.01 degrees. It might, Roy, I've learned that it's somewhere around 0.005.
Okay.
There, it just recorded. So now it wants us to manually enter the full scale. So I'm going to call the control room and I'm going to key in 150.4. Let's see how that looks. Oop, it's failing, but this temperature dropped. So I had this kind of in my head to put this number in. I'm going to wait for this to come up. So this is a little quirk in our dry block. It shouldn't stop controlling.
But if this were real, then we would sit here and wait for it to become stable again. And it's only that we're doing a live webinar that we're trying to hurry things along. So this is, it's not fair.
Okay, thanks, Roy.
So go ahead and take, yeah, good.
So the stability is still below 1. But yeah, for brevity here, let's go ahead and accept this.
Okay.
And it's warning us that we're cutting a corner.
Yeah.
But everything passed. So this is the summary for the temperature element and the transmitter where we're checking the temperature versus the milliamps. We had a maximum error of under 0.3 degrees.
Okay.
And I'm pretending to be Peter Parker today. And here's where we do have a bit of an offset on the span. So probably ought to trim that. And then there's the data that's ready to be sent back. So I'm gonna save this, and I'll save it as found. I had some previous data in there. And then here's the loop, temperature loop, and it was off by minus 0.4 instead of plus. So Peter Parker gets credit. So this one is off. So when I was working with my food customer, we saw this kind of phenomenon, and I was like, what's going on? These numbers should be together. And he goes, well, the DCS input card needs to be adjusted. So really to fix this, we need to really do both. We need to do the RTD transmitter as a combo and then verify that the 4 to 20 is working right. But I'll save this one also as an as found.
And this might be something that isn't obvious, that you can have an offset in the DCS and it's not related to the transmitter. So, but the only way to know is to grab all this data. So, and you grabbed information on the transmitter, you grabbed information on the DCS, and you can see where they're different. And you could go into the DCS and do an offset so that it showed exactly 150 or exactly 40.
And with this kind of equipment and test methods, you can really display a very close to true temperature in the control room. You can really do some accurate work. In fact, here's an example certificate of what you just saw. And I mentioned earlier, this half a degree is really tight. This little guide here at 0 and 100%, this is showing how accurate the calibrator with the test probe is. So you can see we have about a 4 to 1 ratio here. The calibrator standard is 4 times more accurate than this half a degree. So this is really pushing limits here. And
that's a visual representation of the uncertainty of the test standard.
And if you had your paper form, you would have written down these kind of numbers. And I don't know, notice this is out to 3 decimals on the temperature and 4 decimals on the milliamps. So that's an example of the transmitter and probe married together. And then here's the loop. So the loop was below. So there definitely is an offset between with the 4 to 20 and what's being measured in the field. So we got some work to do to make this look a little better. But this is, this is kind of real stuff. Oh, it's showing traceability here, and there's no calibrator on the output because that's just our eye. It's the human is the uncertainty there. So Peter Parker's our output calibrator, if you will, in the control room operator. Okay, so hopefully you've seen some dynamics here when you're working with a dry block out in the field and how it interacts with milliamps. So I'm going to close all these things down. And so we're going to switch channels here and talk about some parameters specific to temperature. So those professionals out there that are calibrating thermocouples and RTDs, we want to talk a little bit about what's this Callendar van Dusen thing and what's ITS 90.
Okay, these are a lot of big words. Can you put it in a, oh, this helps. All right, I just needed some numbers.
Well, just, in the most simplest terms, thermocouples are accurate to so many degrees. RTDs are accurate out to tenths of a degree. Certainly, if you have a 3-wire RTD, it might be closer to 1. If you have a 4-wire RTD, it's closer to 0.1. But you can also buy more expensive RTDs and have a special calibration done against those. And there's a long time formula out there called Callendar van Dusen. So with that formula, you can get out to hundredths of a degree. And if you're really after high accuracy temperature, there's an ITS 90 formula, and it gets you beyond even thousandths of a degree.
If I could say one thing, that
yeah,
we will admit that this is an oversimplification, but this is just an example of the differences in these items from a high level.
Right, and you should know that there are tools that you can utilize. And if some control engineer says, hey, we got to have hundredths of a degree or thousandths of a degree control, you need to tell them, well, you just can't do that with any piece of test gear. We're gonna have to get some reference probes and spend a little extra money. And the more decimals, the more money you spend. That's the other rule. And Callendar van Dusen's been around since 1925. Mr. Callendar was a British physicist. He came up with this third order polynomial formula, and Mr. van Dusen's an American, so it was a across the pond partnership. But van Dusen focused on the freezing, the below 0C correction. So you put those two together and you have a nice formula. And it worked very well up till about 1968. So then the metrologists out there said, hey, we've done some work and we got a much more complicated formula, but it's more accurate. So things were changed in 68, and then more work was done, and test equipment's getting better and instrumentation's better. So today, the ITS 90 polynomial is a 9th order polynomial above freezing, and then a 12th order polynomial below freezing. So just some insight on what's going on here.
So if I could say one thing, as far as the ITS 90 and the Callendar van Dusen, it's an advance on a standard RTD curve. And you'd think the temperature that an RTD curve would be perfectly linear but it's not. And the CVD and ITS 90 are characterizations. It allows you to characterize that curve so that where it's not exactly straight, maybe it dips down right here, and that's how you take advantage of these calculations and get it even more accurate. So this characterization is important.
Yeah, in fact, I've kind of learned from our metrologist, Tony, that if, the ITS 90, it's maybe a bowed kind of curve on a graph. And the Callendar van Dusen correction kind of is a sine wave along that curve, if you can see my fingers.
Yeah.
So sometimes the Callendar van Dusen calculation is a little higher than the ITS 90, when it's crossing, it's spot on, and then it goes a little negative. So it's kind of interesting how these things work.
Curious.
So if somebody tells you they want to measure something super accurate, you need to get a calibrator or meter that can support the ITS-90 coefficient, and then you need to buy a probe. And these probes start really around $500 and can go up to above $2,000 for these super accurate RTD probes with the coefficients. And you have to get them tested every year, and that costs extra. All right. So another thing we want to talk about is a thing called RSS, root sum of the squares. And this is a way, we did a loop test today. So this is a way to, how do you combine all the elements of the loop and come up with a total test tolerance or accuracy, field accuracy that you're trying to achieve? And I just kind of pulled these numbers out of the air. And these are really sort of vendor numbers. I'm saying that the RTD is plus or minus a tenth of a degree. So it's maybe it's a 4. I'm using a 3-wire. I probably should made it a little higher today. But the transmitter is a 0.1% of span. So our span was 0 to 150. So we converted that to plus or minus 0.15. And then I'm saying the DCS input card is like the transmitter.
So you have a tolerance for each item, and then we add them up? What?
Well, some people do. So if you're real conservative, you would say, hey, I'm probably, if everything went and drifted in the same direction and it was off in the same, to the fullest,
okay,
I could still expect to get 0.4 degrees. So that's kind of to me, that's punitive to do it that far. So
okay.
Here's the RSS calculation. You square each component, you get this crazy number. Oh, and I didn't update the slide. You take the square root of 0.55 and you will get an average. This is like I call it a statistical average of 0.234. So it's not as bad as the 0.4, but it's not as good as any of these single elements in the loop. So now this is sort of math, right? It's kind of crazy, but I'm going to say, well, maybe we should say we're within 0.5 degree. So that's what we used on our test today. But there's another factor that comes into play. So I'm sure most of you out there have heard of that you want a 4-to-1 test accuracy ratio or test uncertainty ratio, just depending on whether you're a metrologist or just looking at your equipment. And so this means in practice, best practice is to have a calibrator that is 4 times, or a calibration standard that is 4 times more accurate than the equipment you're trying to test. So with that in mind, if we take this 0.5 degree and divide it by 4, that you need calibration equipment that's accurate to this level in order to test something to that level. Does that make sense?
So what you've done is you have answered one of the questions that we get all the time, which is, I have this thing, what should I use as a calibration tolerance? And you worked it from from the end and went back to the beginning. What's the accuracy of each individual item, whether it's one transmitter or whether it's a loop? And then once you have that number, then you could multiply that by, or divide that by 4, multiply it by, carry the 1, to determine how accurate your standard should be. Your standard should be 4 times more accurate than what you're trying to measure.
Right, and management needs to understand this costs money. The lower the closer you are to 0, which is perfect, the more it's going to cost you. And it's going to cost you in time, to set this dry block up out in the field and to pull the RTD out of the process and shove it down in the insert. And then you got to sit there and wait, time is money. And there's just a lot of components to achieve good performance out in the field. So
Yeah.
so hopefully we've demystified a little bit of it.
So let me just share something. If you've ever wondered about what keeps Ned up at night, or if you're ever talking to Ned and he does this, he is thinking about this set of formulas right here, root sum of squares, or this is what's going on in his head. So I always knew it.
I got up at midnight and was thinking about this.
Yeah.
That's exactly right.
Secret's out.
So anyway, this is just another hack, you know, taking all this stuff into consideration, and how can you, you know, make a good quality measurement out in your process. All right, so let's talk about some more hacks, Roy. And we invite you to share your hacks with us. Teach us something. You know, you guys know tricks and ways to skin the cat.
Hey,
So,
hey.
Oh, sorry.
Yeah, I like cats. Okay.
Sorry. It was just a saying.
Uh,
All right. So we kind of we touched on this already. And, you know, I like this. I personally like to use this word practical when I'm talking to people. Like, you know, why are you testing it at 0? And if I ask that question, most times people go, I don't know, or that's just how we do it, you know.
yeah.
Um,
Or
and
maybe
all
even
I'm saying,
you're doing a 5 up down. Do you really need to?
Yeah. So, you know, so I say it's okay to be lazy, but you need to back up what you're doing, you know. So it's not that you're lazy, you're just working smarter.
I prefer efficient.
Oh.
Economy of motion.
And yeah, and so make things easier, you know. Maybe you don't have a dry block that can go down to the low temperature. It's okay.
Yeah,
You
is
know,
that necessarily a problem?
yeah. Yeah, if we go back to our graph, it was kind of a downhill slope. I mean, you could just keep drawing that line and it would show you what the error was at 0.
Yep.
So you can be very confident when you do this kind of testing. And especially with a dry block, you want to do test points that reflect the process operation. The range of the transmitter, the range of the RTD or thermocouple is really irrelevant. Where does your process run? And you know, you kind of want to pick a low temperature of the possible process, the maximum temperature of the process, and then in the middle. And you don't even have to do the middle. If a critical reaction occurs at 60% of that window, then maybe that should be your middle test point, because that's the most important number on the piece of paper.
Yeah.
Okay. So then we showed you this RSS thing, and you kind of alluded to it, Roy. Sometimes you need to kind of work backwards. You kind of say, well, okay, what can I do? What's the best that I can do? And therefore, what can I achieve, especially with this 4-to-1 ratio?
So one comment on that. So what's the best I can do? Maybe, so our standard is a good to 1/8 of a degree, or 0.125, and we're shooting for a 1/2 degree tolerance. But you know what? Maybe the process says that whatever's flowing through this pipe can be plus or minus 10 degrees and still be fine. That means that the 1/2 degree that you're aiming at is not even necessary to go that tight. So you have some wiggle room. So the answer to what should my tolerance be is it really depends, but you should have input from the engineering side as well for the process.
Yeah, it's kind of a negotiation, right?
Yeah.
You know, the technician they want plus or minus 10 degrees for that example you just gave. That would make their life easier. But, you know, the control engineer that's overseeing quality of products is going to say, well, that's not good. You know,
Yeah.
so if you could do something to 1 degree or 2 degrees as a kind of a goal, that's going to make things, then you don't have to do all this dwell time that we were showing, and you can move much quicker through the test. If it's close to 0 error, you're happy. If you see 0.3 out of something that's got to be 2 degrees,
yeah,
move on.
That's probably one of the biggest hacks you can learn from, is that if you don't need to be aiming at this little tiny target, but you have it larger, then it's much easier on everybody.
Yeah. And since we're talking temperature and the instrument, what's the benefit of a 3-wire RTD versus a 4-wire RTD? The
That's a
cost,
lot of decimal places out. Yeah.
yeah, the cost isn't that much different. And that would be one way to improve your measurement accuracy. So, all right. So what's our next hack? Hack. So this is complicated, Roy. Can you explain this?
Seriously? So if you do calibrate your loop from beginning to end, then you know that there's well, you have an offset in the transmitter and you have an offset in the DCS card, but maybe you do the loop where you only do the intro point and the outro point. Is that a thing? So if we would have done the temperature on the probe and then only recorded the display in the DCS, we could do that. And if it was a third of a degree off, we could do an offset in the DCS of a third of a degree and essentially calibrate or correct that value so your DCS is right on the money.
That's true. And it would be a time saver. And as an example, anybody out there that's maintaining a flow computer, if we have any flow computer folks, like pipeline people, and that's exactly what they do. They just make adjustments in the computer. They do not touch the transmitter. They don't worry about the probe unless, there's a problem with the probe. If the probe needs to be replaced, they replace it, but then make an adjustment in the computer. They don't, it's really simple, and it helps you make a very accurate measurement.
Yep, and it's thinking outside the box.
Exactly. So use this concept if somebody's pushing you for better accuracy in the control room. And then obviously we've already covered this base, but you need to think about using a more accurate reference probe that has either Callendar van Dusen or ITS 90 coefficients if you're trying to get out to this level. It's really the only way to do it.
And one comment on that is that there was a question earlier about what's a dry block, and a dry block is simply a temperature, a unit that generates temperature, as opposed to a bath, which uses a liquid.
It's a heater or a chiller. Yeah.
So, all right, I lost my train of thought. What I was going to say was, every dry block is accurate to a certain value, and you can usually increase that accuracy by using a higher performance or more accurate temperature probe to use that as your standard in that dry block or bath. And that's Ned's whole point here with using a reference probe. You can upgrade the accuracy of your temperature measurement by using a high accuracy probe.
Very good. Okay, we're getting to the end here. Sometimes it's not easy to pull the probe out of the process. It could be it's mounted in a weird place, or it's all corroded, and to actually remove that field probe would cause more harm than it's worth. So another consideration is install a thermal well that's right next to the probe, and heat treating people with furnaces do this all the time. So you can just walk up to that thermal well, stick a thermometer essentially in there that's traceable to NIST, and compare the process reading to your field thermometer that you put in the thermal well. So it costs some money to do that, but it can save you a lot of time and headache and just allow you to verify that things are running well. And finally, you can always throw a probe away. I know a lot of you out there, if you question that the RTD or thermocouple's bad, just put in a new one. They don't, especially if they're cost less than $100. But if you use this concept of trimming either the input card or the transmitter, you can get more life out of your probes and still get a very accurate measurement. Because even if you replace it, you need to check what's that loop indication. So you're going to do that work anyway. So you can learn with your probes how long they should really last for a given process, and maybe you can get some more mileage out of it and save some money.
Okay, by utilizing an offset.
Okay, so to wrap this up, we have two examples. I'm going to let Roy talk about this one. What is
Seriously,
that?
you put up a picture of beer and asked me to talk about that. All right, so
Well, that's what you told me.
so this example was a brewery, and a rather large fermentation vessel. So one thing about calibration is that in determining on how accurate you need to be temperature-wise, there's a value where your product becomes unusable. If you have a beer and you have a fermentation process in there, you have to get the temperature up to a certain value in order for the fermentation to start. But then as you increase, okay, fine, it's working. But if you go too high in temperature, here's where you kill it. So you have to operate within this range. And that's where you need, that'll help you determine how accurate of an should you be calibrating to maintain that proper temperature. And in this case, well, it was still usable as a product, so they closed off the valve, but they directed this vessel into a canning operation of a cheaper brand that they sold. And I won't say any names at all, but that happened.
Well,
Otherwise, if you do end up killing it, then you got to open the valve and then dump it down the drain and just empty
and
it all out.
that would make everybody cry.
Yeah.
The brewer and the customers. So, so yeah, if you have these critical temperatures, you can't mess around. You really need to know what's the right temperature. So here's another example that I had with a customer down in Florida, and they had a process where they had 6 zones. So they had 6 RTDs, essentially 6 personalities coming into their 8 or 6 DCS cards. So, so the temperatures were all over the place, and they were having a lot of quality problems. And they utilized a dry block and did exactly what we said doing this offset. They made, when with the 6 probes in the dry block, and set at the critical temperature for their process, they made that DCS read all 6 zones the same. So then when you install these back into the process, they knew they were seeing the same temperatures across the board. So if they adjusted zone 1 to go up in temperature to match zone 6, they knew that they were in sync. And it actually increased their quality and their throughput by using a dry block and doing this offset thing. So these are real deals.
So temperature probe 1, if that one measures 2 degrees low, then they go to the DCS and then they put an offset of +2 to make it perfect?
Exactly. And
they just did that on each of them.
But it wouldn't be that bad. I mean, but they were seeing problems like, it was maybe this one was a 10th high, this one was pretty good, this one was a 10th low, this one was too high, 2/10 low. They were all close, but it was causing problems. And now they could really tune things knowing that they were getting identical numbers coming in.
Okay. And part of your point is that you don't have to throw these probes out and get more accurate ones.
Yeah.
If you know what they're reading, then you can put that offset in and have some reliable numbers.
And so this kind of application would definitely want to get some 4-wire RTDs. Spend the extra money to get, then you'll really be tuned in on what you're trying to do.
Okay.
So, all right. So I think we're done, Roy. What time is it? Oh, we ran late. We're a little long. Sorry about that. So just to reiterate, our initial point was trying to be practical and take a step back from what you're doing and try to analyze, look for best practices, find a better way is all we're trying to advise here. You also need to know your sensors and instrumentation, and understand what's the benefits of a reference probe, when to try to use it. And we have a lot of customers, they try to set tolerances where they don't have to use a reference probe. So, So when you can get by with 1 or 2 degrees, then you don't need a reference probe. So
don't overcomplicate it.
Exactly. And we're using the term hacks today, but these are how do other people do it? If you're a large company, you've got the same process at another site. I mean, you guys should be doing things the same way. Find out what your peers are doing, and also look to your vendors as a resource for good information, for best practices. And then Roy likes this term. If you know what you're doing, you're going to have a lot of confidence and can stand up to any questions and audits and all those kind of things.
Exactly. And so one thing as far as networking, it is outstanding to get information from your peers and how are they doing things. And it's not a who does it better, but it's a how can we learn from this? And with that, we do have an ACE conference coming up, an annual calibration exchange. And let's see, do we have a video on that? Should be playing shortly. All right, excellent. So as you might imagine, we're changing this event from an in-person to an online calibration exchange. And I'm guessing we're going to have links on here if you'd like to join us, but those will still be on the same dates. What was that, September 16 and 17? And it will be an online calibration exchange. So more details to follow. With that, I guess we'll take it to our Q&A. Scott.
All right. Thanks, Roy. Thanks, Ned. We are going to grab a couple questions here before we have to sign off. So I guess to start out with, there's one question that I was wondering if you could address real quick is, can you give us an example or two of some situations where you might use the Callendar van Dusen formula or polynomial?
Well, I'll answer that one. It's Callendar van Dusen's getting to be more and more passé, but it really gets you accuracy out to 2 decimals. So it is simpler to utilize and maintain, and a lot of vendors are actually using Callendar van Dusen in their instrumentation, because if you're accurate out to 2 decimal places, that's plenty good for many applications. But yeah, I would say the ITS 90 requires an extra test point or two, and it gets rid of that sine wave effect. So with the crunching of ASIC chips and computers, whether it's a 3rd order polynomial or a 9th order polynomial, it doesn't matter as much anymore. But
if I could add one thing on probes with these different curves, you will be given the curve from a proper calibration lab, because they're going to put that probe in and they're going to measure it over different temperature points, and then they'll plot out what that curve is. So that's how you get the ITS 90 or a CVD curve.
Yeah, but that's a quick explanation or answer.
Yeah.
I guess all things being equal, go for the more accurate one. If Callendar van Dusen can save you some money, go with that if it's accurate enough.
All right, good. So the next one is has to do with whether you guys have or could share any experience in calibrating cryogenic temperature transmitters. The questioner mentions negative 250 Fahrenheit. Any experience there?
That's in the South, we call that dang cold.
That's
What
pretty
is
specialized.
250F to 100C, minus 100C? Is that, I don't know that number in my head. There are units out there that use helium through a vortex and they get to over minus 100C. So I don't, so again, I would use a device like that can do these very cold temperatures, and you might have, if it doesn't go all the way to the minus 250F, you're going to have to interpolate, but you could, get it, at some higher temperature, go all the way down as cold as it'll go, and you can pretty much say that it'll keep going on that line. Remember that ITS 90 was a 12th order polynomial when it was below 0C, and it's a 9th order polynomial when it's above 0C. So getting cold is tricky, and that's an extreme temperature. But
Yeah.
But if you want to email me later, I could hook you up with the models that can do the at least minus 110 or minus 120 C.
All right, very good. All right, so another thing that I was kind of curious about that came in was whether you could explain the concepts of tolerance and accuracy and just kind of draw some distinctions there and lay out the nuances for them.
So I think at that point we were talking about determining what tolerance you should use, and I guess I was at that time of speaking, I was referring to those two as interchangeably, but more often is looked at accuracy versus uncertainty. And so I wonder if that is more of what the question is. You have accuracy that's of a certain value, and uncertainty includes other variables to be a more complete representation of what is in question.
We did have an earlier webinar. We're going to give you a link to that. We did touch on that. So that's a whole nother topic under itself. But in heat treating, I'm working with some folks that are doing heat treating, and the AMS 2750 specification talks about accuracy. And it talks about that your standards have to be more, 4 times more accurate and things like that. And, a metrologist talks about uncertainty. So it's almost like 2 different things. But to me, if you use the term accuracy, that's kind of an off-the-shelf number. It doesn't really include a long-term stability number. Some people say here the additional error for 6 months or 12 months is blah. So uncertainty typically includes, a time component. It also includes the reference standard. So the uncertainty number is going to be up here, and the accuracy number is down here. So vendors like to use this good number.
Yeah.
But reality is up here. And we were kind of getting into that. In the RSS method, we were using accuracy numbers. We came up with 1/4 of a degree or so, but we loosened it to 1/2 degree, which is really the best. We kind of backed into it. It's the best we could do with our gear. But we talked about this, that the tolerance needs to be, what do you need to make a good quality product in the safest manner and the most efficient way? And
Yeah.
giving up on the tolerance it's going to save you time. So it's this negotiation of what is a good tolerance.
Yeah, so in that case, I would take back that using them interchangeably, but tolerances should be more of what's a realistic number that you should, what's reasonable.
And also, if you document, if you're doing some documentation and building some history, you can see what you're actually doing. So if you set it at 2 degrees, but then you start tracking it and you see, hey, we're down near a half a degree, you could easily lower your tolerance to 1 degree or even tighter, because you're already kind of achieving it. And on the same token, if you've got it really tight and you're always adjusting, maybe you need to back off a little bit on the tolerance so that you can get things in control.
Or buy a more accurate piece of gear or instrument.
And that costs, yeah, more money.
More money, yeah.
More investment, but yeah. Okay. Yeah, it's
All
it's a whole nother webinar.
Yeah. All right. Well, yeah. We are kind of over time here, but we're going to try to squeeze in 1 or 2 more here.
Yeah.
So, what about the? Can you talk about the frequency of calibration? Some of the things that might help guide people in terms of how frequently they should be doing these things.
Well, that's another webinar topic. I've actually written a paper on intervals, calibration intervals, and I say the best way is to document. You know, if you can, and you don't need to document everything, but if these things are really critical, you know, where are you today? Compare that 6 months down the road, 12 months down the road, and bottom line is you have random noise. So when things drift, sometimes they're up, sometimes they're down for ambient conditions. But if you're seeing a trend, see, I got to go this way. So if you're seeing a trend and it's going, you know, in an upward direction, say every time you go out, now you can kind of predict, and you can look at your interval and see, you know, do you need to go out every 6 months before it's out of control, or can it go 2 years? I think in general, people over calibrate. They go out too often. And so by documenting, you can kind of optimize. So some things you maybe need to do more frequent, but a lot of things you can probably back off. But then there's situations where you're mandated to go out every quarter or every 6 months. So sometimes you don't have that luxury.
Yep.
Great. All right. So let's do a last one here. So what about this one about do we require calibration even if the instrument is not malfunctioning?
It's another good question. So Ned, what do you say to that?
Well, I mean, we have customers, Roy, that say they haven't checked something for years, you know, and it's rocking and rolling. And maybe that's where you need like this thermowell idea. If you could just do a spot check, you know, on a temperature, that, and is, you know, and it doesn't have to be within even 1 degree. If it's within 5 degrees, especially on a thermocouple, you know, you can leave it alone. So that's a good goal, is not to calibrate it if it's not malfunctioning.
So with that, there are cases to where you don't really, it doesn't matter what the exact temperature is, or you just need to know that there's temperature for this item on the loop. I've seen some cases where going from calibrating it annually to a run to failure, which means, all right, we're not even going to calibrate this because it's not critical to the process whatsoever. Maybe it's an ambient temperature thing that's a comfort level for a controller, or but it just doesn't matter. So you run it till it fails and then you replace it. So I think the answer depends on the criticality of what you're proposing, of what you're actually looking at, criticality to the process on if you should calibrate it and how often.
Yeah, and if you can come up with a clever way to kind of verify it, you're not really calibrating it, but you're just verifying that it's in the ballpark.
Yep.
Then that ups your confidence level, so you can ups your confidence level, so you can.
All right, great guys. In the interest of keeping people to their schedules for today, we're gonna try to wrap this up. So if we didn't get to the question on the air, there's contact information you can see on the slide here. So you can always email the presenters using those emails here. Also, if you missed a portion of the webinar or you want to watch the recorded version, again, there's going to be an email with links to all the recording and the supporting information. Also, just wanted to mention the webinar that Ned mentioned just now occurred earlier this year. It was called Basics of Temperature Calibration. Ned and Roy did that one together as well. If you want to look at that one, that's also been archived at www.chemengeonline.com/webcasts. You can see the link there too on the slide, but that contains the earlier webinar, and it will also have this current webinar. And last reminder, there's going to be a survey popping up, including questions about next topics that you might like to see. So before we sign off here, just want to thank Ned and Roy for their expertise and their time here. Thanks for all the attendees for sticking with us here, and hope you can join us again for a future webinar. Thanks a lot.
All right,
Thanks everybody.
Scott. Be safe.